Okay, welcome to our lecture on the one-way between subjects analysis of variance. This will be an extension of what we've covered previously in the independent samples t-test, and this will now allow for us to compare more than two between subjects groups at a time. So we'll be dealing with a situation where we have an independent variable that has two or more levels. It's a between subjects variable, meaning individuals are in one case or in one group, but not belonging to any of the other groups. And the dependent variable will be an interval or ratio variable, basically a quantitative variable that we want to compare the means across the levels of the categorical independent variable. So, as I said, for studies with more than two levels of the independent variable, and we want to compare the means, the t-test will no longer be appropriate. The reason is the t-test only compares two groups, so it only makes basically one comparison of two means. We could, if let's say we had, for some reason, an experiment where the independent variable had four levels, we could conduct 6 t-tests to test all pairwise comparisons. So let's say there was level A, B, C, and D of the independent variable. We could run a t-test to compare A to B, A to C, A to D, B to C, B to D, C to D, right? And we could cover all of those with t-tests, but it would present some problems. The biggest problem that would present is what's called inflation of type 1 error. So roughly speaking, there's more precise calculations for this, but roughly speaking, if we conduct 6 different t-tests, we would be inflating alpha basically by 6. So we could take our alpha, whatever it was. If it was 0.05, most likely we could take 0.05 and then multiply that by 6, and we would find that now our probability of at least one type 1 error, even if all of our tests are independent, it's a lot higher than we would like. It's about 0.3 or 30% of the time. If you've ran 6 tests like that, you would make at least one type 1 error. So that's probably higher than we're willing to be comfortable with. So here you can see kind of a graphical depiction of what I've been talking about. With the more hypothesis tests you perform on the same data set, so this is assuming that they're independent, which they may not really be, but let's just pretend that we're doing a bunch of hypothesis tests on the same data set. As you can see, as the number of hypothesis tests increase from 0 to 5 and 5 to 10, the probability of at least one type 1 error jumps dramatically. So if we were doing 5 hypothesis tests, the probability of at least one type 1 error would be roughly 20%. If we were doing 10, roughly 40%, right? And at a certain point, it becomes basically you're almost guaranteed to make a type 1 error, right? So there's different ways to deal with that depending upon the situation. We're going to deal with it in two kind of related ways for the situation where we're comparing means across the number of groups, and that is to deal with it by doing what's called an analysis of variance, which is the topic of this lecture, and then also to deal with follow-up tests for the analysis of variance with type 1 error correction. So we're going to go over one method of doing a follow-up test, or what's often called a post hoc test, to follow up an analysis of variance to determine where the differences actually are by correcting for type 1 error. Now, I do want to warn you that the topic of ANOVA is one that could be could provide the content of an entire course rather than one lecture. So what we're covering is called the one-way between subjects analysis of variance. There are various types of analysis of variance, but this is sort of the jumping off point for understanding what analysis of variance is all about. So as you might guess, there are also within subjects or repeated measures analysis of variance. There are also situations where you might have between subjects and repeated measures variables in the same analysis of variance. There are situations where you might have multiple between subjects independent variables in one analysis of variance. So each of those types of analysis of variance is a little bit different than the one we're going to cover in this lecture. In this lecture, we're going to stick to the most straightforward analysis of variance, or ANOVA, called the one-way between subjects analysis of variance. And one-way just means there's one independent variable, and between subjects means that that independent variable is a between subjects independent variable. And of course, the independent variable will have several levels, often more than two levels, right? So it's important not to confuse an independent variable with levels, right? The levels make up the variable. The variable itself is made up of levels of the independent variable. But in this sort of ANOVA, there's only one independent variable. And something called a factorial ANOVA, which we're not going to cover in this lecture. A factorial ANOVA is made up of several independent variables, and something called a mixed ANOVA is made up of several independent variables where some are between subjects and some are within. So I just wanted to let you know that this is just a small part of a much bigger picture of ANOVA type designs to test hypotheses. Basically, ANOVA is almost always testing hypotheses about differences between means. So we'll use the one-way between subjects ANOVA when we have a between subjects design with one independent variable that has two or more levels. Now, if the independent variable has two levels and is a between subjects design, as you already should know, you can use the independent samples t-test. However, if there's more than two levels, we'll have to use the ANOVA. If you use an ANOVA in a situation where there's only two levels of the independent variable, it will be identical. Your results will be nearly identical if you do an ANOVA as compared to a t-test. Basically, the F value that you get, that's the test statistic that we're going to use for ANOVA. The F ratio that you get, it will basically equal the t observed squared, and the p-value will be identical. Now, with an ANOVA, we're comparing means across the levels of the independent variable. The dependent variable should be interval or ratio. It should be a quantitative variable. ANOVA does not work if the dependent variable is, let's say, a binary presence or absence variable, and it's not well suited to deal with ordinal variables either. So it's assumed that your dependent variable is interval or ratio, or at least reasonably continuous or quantitative in nature. So we don't want to have an outcome being, does the person live or die, or does the person pass the class or fail the class? That wouldn't work in an ANOVA type design. We'd have to use a different sort of analysis for that. We also continue to have the assumption that the within group variance is the same across the levels of the independent variable in their respective populations. So basically, we maintain the homogeneity of variance assumption, or the similarity or equality of variance assumption. So we're basically assuming for the ANOVA, because we're creating an error term, which is basically assuming that the error in each group or condition is the same, or at least reasonably similar, we want to be able to check the assumption that the variances within each group, so let's say there's three groups, the variance in group A, the variance in group B, and the variance in group C, should be reasonably similar in our samples, and we're actually assuming that they're the same in the population. Now, for our purposes, we're not going to get really bogged down in testing assumptions, but for our purposes, we're going to say, well, if the largest mean is not 4 times or greater than the smallest mean, the largest variance is not 4 times or greater than the smallest variance, then we're going to basically say, okay, we're just going to assume that we've met the homogeneity of variance assumption. So we're not really going to be focused on testing that assumption, but at the same time you should be mindful that it does exist for this sort of ANOVA design. All right. So here's a silly example or soda example from the t-test chapter that will extend to the ANOVA design. So let's say we had a group of people and we wanted to see, okay, are there differences in taste satisfaction across these different types of soda? We have American Coca-Cola, Mexican Coca-Cola, and RC Cola. So people show up to the experiment. It's a between groups design. So they're randomly assigned to one condition, right? Only one. So this person shows up, they're in whatever group they're randomly assigned to. Next person shows up, they're in whatever group they're randomly assigned to. So they're only tasting one soda, and then they're subsequently rating the dependent variable, their taste satisfaction with the soda. So in the end, we'd want to compare the means to see if the differences between the means are greater than what we would expect by chance. Basically, we want to reject the null hypothesis that the means are all equal, that the taste satisfaction from each soda is equal. If we reject that, then we can say that there's at least one difference between the means. With regard to the homogeneity variance assumption, we're assuming in order to run the ANOVA that the variability within each group, so the variability within American Coca-Cola, Mexican Coca-Cola, and RC Cola, we're assuming that the variability within each group is the same in the population and reasonably similar in our sample. As I mentioned, the null hypothesis for this ANOVA will be that the means in the population are the same. So that's the null hypothesis. The alternative hypothesis is that there is at least one difference. So there may be more. There may be more than one. But if we reject the null, we can say that there is at least one, maybe more, but at least one difference between the means. So we'll be using a new distribution called the F distribution. And basically the F distribution, the shape of it, the good news is we don't have to deal with negative values because the F distribution starts at 0. So it doesn't go below 0, so we don't have to deal with negative values. The F distribution, the shape of it depends on the degrees of freedom in both the numerator and the denominator. So the numerator sometimes is also called degrees of freedom 1, or degrees of freedom effect, or degrees of freedom between, depending upon which book you use. But that's basically the top one, the numerator degrees of freedom, is one of the determinants of the shape of the F distribution. And the denominator degrees of freedom is another determinant. The denominator degrees of freedom are sometimes called df2 or df error or df within, but it's basically the bottom one, the denominator degrees of freedom. So you can look these up in the back of the textbook. There's a table where you can look up, okay, if my degrees of freedom 1 is, or degrees of freedom numerator is 3, and my degree of freedom denominator is 50, what is the critical value? In other words, for let's say alpha 0.05, what F observed value would I need to achieve to be in the significance region or the rejection region to be able to say, okay, I reject the null here. And in a minute, we'll talk about how we determine numerator and denominator degrees of freedom. But for now, just know that that determines basically your F critical value if you're doing this sort of thing by hand. In addition to the calculator in the back of your textbook, there's also one posted on Blackboard where you can simply either enter in the degrees of freedom and the alpha, and it'll give you the F critical value you need to achieve to reject the null, or you can simply enter in an F observed value that's the result of your ANOVA calculation, and it will give you the corresponding p-value, and you can compare the p-value to the alpha to determine if you are going to reject the null hypothesis or not. Alright, so taking a step back and looking at analysis of variance a bit more conceptually. So with analysis of variance, we're basically slicing up the total variability in the data. So we could think of total variability or total variance, or for now we'll just say the sum of squares total, is basically the sum of the square deviations of the scores around the overall mean in the data. So ignoring group membership, just basically what's the sum of the squared deviations from the mean? What's the sum of the squares? Now, that's made up of two components. One would be the effect variance, or the sum of squares between, and sum of squares between is basically the sum of the squares deviations of the group means. So now we're paying attention to the groups, and each group has its mean. Sum of the squared deviations of the group means around the grand mean, so the overall mean. The grand mean is the overall mean, ignoring groups, and the group mean is the mean within each group. So the effect, or SS between, is basically to what extent are the group means varying around the grand mean. Now if you think about it, if the group means are not varying very much around the grand mean, then there can be really no effect of the independent variable because there's no differences in the means between the groups. But just because there are differences between the means between the groups doesn't mean that they're important or quote statistically significant differences. We also need to take into account the error variance, and the error variance is basically computed by taking the deviations of the individual scores within each group around the respective group means. So let's say of the people assigned to group A, each individual case, what is the squared deviation of that individual case around its group mean? So we have intra-group. So SS within is intra-group variability, whereas SS between is inter-group variability, and SS total is just overall variability ignoring group membership. So just like almost every analysis we're going to cover in this course, we're basically trying to determine, well, what proportion of the variability is effect, is signal, and what proportion of the variability is noise or error. And if we add up the effect, or the SS between, and the SS within, they will total, if we've done our math correctly, they will equal the sum of squares total. So let's look at the computations for this. I encourage you to do this by hand once, maybe twice, just for fun, but you're really going to want to focus on the SPSS computations of this because it will save you a lot of time and likely, if you set everything up properly, be much more accurate than if you do this by hand. But basically, to compute a one-way between Subjects Anova by hand, you first should set up one of these tables, which is called an Anova table. So we'd start by computing SS between. So we want a row for between, within, and total. We want a column for source, sum of squares, degrees of freedom, mean squared variance, and the F ratio, F observed. So for between, right, this is where things get a little murky, but we would want to compute the sum of squares between. Now this formula here is a computational formula, so it'll be easier to follow than the conceptual formula in terms of hand calculations. So I've skipped the conceptual formula here, and we're just going to work directly with the computational formula. What we basically have here is we're taking the sum of x for group 1, the subscripts designate the group, the sum of x for group 1, squaring the total, dividing it by the number of cases in group 1, adding to that sum of the scores in group 2, squaring the total and dividing it by the number of cases in group 2, and so on, adding the sum of the scores from group 3 squared divided by the number of scores in group 3. We add those up, and we keep going until we run out of groups, so however many groups there are. And we subtract from that the sum of all the scores squared. So we add up all the scores and then square the total and divide by the total number of scores altogether. Right, so if there's 10 people in each group, little n would be 10, 10, 10, big N would be 30. Once we get SS between, SS within is pretty straightforward because, okay, first we need to square all the scores individually and then add up the total of the squared scores. Then the right-hand part of the equation for SS within is identical to the left-hand part of the equation for SS between, so we can just, as long as we've calculated it correctly above, we can just slide that down and put it in the right-hand side of the equation. All right, once you've calculated SS between and SS within, the rest is pretty straightforward. So we want degrees of freedom between, or degrees of freedom, as we called it in the previous slide. Numerator, this is going to be the top degrees of freedom, is basically the number of groups. So if there's 4 groups, and k is 4 minus 1. So number of groups minus 1. K is the number of groups. The within degrees of freedom is total sample size, right? The total sample size minus the number of groups. So if your sample size is 100 and there are 4 groups, your degrees of freedom denominator, or degrees of freedom within, is going to be, I forget what I said, degrees of freedom, if your sample size is 100 and you have 4 groups, then your degrees of freedom will be, in the denominator rather, will be 6. Alright, then finally you have degrees of freedom total, which isn't terribly important, but you can calculate it by the total sample size minus 1. Also, if you add the 2 degrees of freedom together for between and within, or numerator and denominator, that should equal degrees of freedom total. And again, if you calculated correctly, if you take your sum of squares between plus your sum of squares within, that should get you your sum of squares total. Alright, next we can put this into an average, let's say average variance. So we have our mean squared variance. So we're then just going to take our sum of squares between and divide that by degrees of freedom between. And for error, we're going to take sum of squares within and divide that by degrees of freedom within. Then last step is to get our F observed. To get our F observed, we take our mean squared between, so our estimate of our effect variance, and divide it by our mean squared within, which is our estimate of our error variance, and then we get the F observed value that we can compare to F critical, or look up the p-value for, and decide whether or not we want to reject the null hypothesis that all the groups are equal and support the alternative hypothesis that at least one of the means is different from the others. Alright, so we'll conduct an ANOVA by hand here in a minute, but first, after you complete the analysis, you'll want to compute an effect size measure. Now there are various effect size measures for ANOVA. We're going to use probably the most widely used one and straightforward one, not necessarily the best one, but it's kind of the one that you should understand first. So it's called eta squared, and it's symbolized like so, the Greek letter eta, and it's interpreted as the proportion of the total variance that is explained by the independent variable. So it's literally the sum of the squares between, or sum of squares effect, divided by sum of squares total. So the proportion of the total sum of squares that is between sum of squares, right? The differences between the conditions around the grand mean. So it ranges from 0 to 1. 0 would mean that there is no explanation of the total variance by the independent variable, and 1 would mean that there is perfect explanation of the total variance by the independent variable. In reality, it tends to not be anywhere near 1, and hopefully not too close to 0. If it's too close to 0, then it's likely not a very meaningful effect size, although there are some situations where small effects can be important and meaningful. Like I said, there's many more effect size statistics that exist for ANOVA. One other popular one is called omega squared, which is just a correction to eta squared. For, let's say, eta squared sometimes tends to slightly overestimate the effect size. So there are other ones, but the one we'll use in this class is eta squared, and it can very easily be calculated from ANOVA output or your ANOVA hand calculations by simply taking sum of squares total and dividing that into sum of squares between. Now, if your analysis, your ANOVA, yields a, quote, statistically significant F observed or F ratio, you're going to want to know where the differences are, because remember we said there will be at least one statistically significant difference if we reject the null. There may be more. Now you can probably be rest assured that the largest difference between the means, so whatever means you have, the largest difference is probably very likely to be one that is statistically significant. However, you don't know about the others. And you may not know about the others, and just eyeballing the means is usually not a good way to go. So instead, you will conduct what's called a post hoc test. Post hoc test is a test that is conducted after the main analysis to determine in ANOVA where the differences are. Now the one we will use is called Tukey's honestly significant difference, and there are a multitude of post hoc tests which we're not going to really delve into. We're just going to stick with the Tukey's post hoc test for our purposes. To test where the differences between the means are. So it uses a different test statistic. It's kind of like doing a bunch of t-tests. Now I know I started off this lecture telling you we're doing the ANOVA so we don't have to do a bunch of t-tests. And then we did the ANOVA, and now I'm telling you we're kind of doing a bunch of t-tests. The main difference is, aside from using a slightly different distribution, the Q distribution, the main difference is we're controlling for Tukey's test controls for type 1 error. So we can set our type 1 error at a particular rate. So if we want to control for type 1 error at 0.05, then we can just set our type 1 error control level to 0.05 and proceed with the Tukey's test. So we're going to calculate, if you have a statistically significant difference, then you should proceed and do a post hoc test. If you did not detect a statistically significant difference in your ANOVA, you should not proceed to conduct a post hoc test. It would be not unnecessary. So there's two ways to kind of go about this. One is to start with the largest difference, which is probably guaranteed, almost guaranteed to yield a statistically significant difference, and then keep going to the next one down, so the largest difference, and then you go to the second largest difference, and the third largest difference, and so on, until you find that one is not significant, then you can stop. Or you can start with the smallest. If the smallest is significant, then you know all the ones that are larger in terms of the difference between the means are also significant. Or you start with the smallest and keep going until one is significant, and you know all the ones that are larger than that will also be significant. I usually start with the largest and keep going until I find one that is no longer significant. Or you can use SPSS, which will make the whole process a lot quicker and likely more accurate. So let's go ahead and do all this. Let's put this all together. We're going to conduct an ANOVA on these data where we have an independent variable that is reward type. So students are either getting rewarded with pizza, with stickers, or with nothing, let's say, in the control group. And we're recording how many books the students have read in these different conditions, and we want to see, is there a significant difference between books read if people are rewarded with pizza, or students are rewarded with pizza, stickers, or if they're in the no reward control group. So we're going to run the ANOVA. If the ANOVA is significant, we'll do the post hoc test, the Tukey's post hoc test, and then finally we'll also report an effect size for the overall ANOVA. So first step is to take down the ANOVA table. So you want to create an ANOVA table that looks like this, right? Because we're going to need to fill in this ANOVA table. So we take down the ANOVA table. We should probably, just for fun, note that our null hypothesis is that our pizza condition and and our stickers condition and our control condition each have the same effect on the students in terms of the number of books read. In other words, we want to say number of books read, the mean number of books read in the population. So imagine a population of people getting rewarded by pizza, a population of people getting rewarded with stickers, and a population of no rewards at all. We want to say that those are equal. Basically, that there's no effect of any of the manipulations. The alternative hypothesis, the one we're probably going to reject with these data, or we're hoping to reject, is that there's at least one difference, right? So at least, right, one difference between the means. There may be more, but if we reject a null, we know that there's at least one. So we have to get started with the calculation. So we're going to start with SS between. SS between, remember we calculate by taking the sum of each scores in each group, squaring it, and dividing by n. So let's go ahead and first we need to sum up the scores in each group. So in the first group, the pizza group, we're going to have sum of x group 1 equals, so adding up all those scores, you get 102. Sticker group, adding up all the scores, get 54. And then finally the control group, adding up all the scores, I get 44. Now while we're at it, while we're doing that, we might as well also compute the mean. So we don't need them quite yet, but we'll need them at some point. So to compute the mean, take 102 and divide by 6, because there's 6 people in each group. So we have equal sample sizes here, which just makes this easier. We have 6 people in each group, so we take 102, divide by 6, we get 17. 54 divided by 6, we get 9. And 44 divided by 6, we get 7.33. Alright, so back to the sum of squares calculation. We want to take the sum of x squared for each group and divide by the sample size. So we're calculating SS between. We're going to take, there is a way to simplify this because there's equal sample sizes, but we're just going to stick to the formula that we have. That's 102 squared divided by 6. And this is 54 squared divided by 6, and then add, so there's 3 groups, and then we have 44 squared divided by 6. And then last step is we're going to subtract the total score squared. So we don't have the total squared yet, but we can get that quickly by taking 102 plus 54 plus 44. So 200 squared divided by 18, which is the total sample size. Oh, we're running out of room. 200 squared divided by 18, right? Total sample size is 18. So we just carefully use order of operations, and we'll have our sum of squares between value calculated. So 102 squared divided by 6, 1734, plus 54 squared divided by 6, 6 plus 44 squared divided by 6 is 322.66. That's the left-hand side of the equation, and then we're going to subtract 200 squared divided by 18. It's going to give us a lot of 2's. 22.2222. Alright, so now we can get our sum of squares between by adding those numbers together. 1734 plus 486 plus 322.6667 gives us, so we're going to need this number again later, so we might as well write this one down. So adding those together, we get 254 and 2542 rather, 2542.6667, and we're going to subtract 2222.2222, a lot of 2's from that, to get our sum of squares between value. And that's 320.4445. So we can now plug that into our ANOVA table, 320.4445. Alright, that fits barely in there. Okay, now we need our sum of squares within. So remember, our sum of squares within, the good news is with this formula, the left-hand side of the between formula becomes the right-hand side of the within formula. So we've already done a lot of the work. We've done the right-hand side already. So now we just need to get the left-hand side, which is, unfortunately, we have to square all the scores and then add up all the squared scores. So many of you may have calculators that make this a bit easier. You can use Excel to make this a bit easier. But if we were doing this kind of the long, old-fashioned way, we'd need to square up every score. Just squaring every score and then going to add up the total of all the squared scores. Squared all the scores, and now add up all the squared scores. So if we add up all the squared scores, I get 2,804. So now we can take the sum of squares within equals 2,804 minus, remember now we're going to subtract the left-hand side from the previous equation, which is 2542.6667, which gets us 261.3333. Alright, so now we have our sum of squares within 61.3333, which can add that to sum of squares between to get our total. Which gives us 581.7778. So our total sums of squares is 581.7778. 320.445 is how much of that is estimated to be from between group variance or effect variance, and 261.3333 is what's estimated to be from within or error variance. Alright, so now we want to get our degrees of freedom, which is k minus 1. K is number of groups, which is 3. So k here equals 3. 3 minus 1 is going to give us 2. And then error is going to be big N. Here, big N is 18. There's 18 total cases in the analysis. Minus 3 is going to give us degrees of freedom of 15. All right, now, to get our mean squared error variance, we simply divide our sum of squares between, not error, effect variance. We're going to divide our sums of squares between by 2. So 320.4445 divided by 2 gives us 160.22. And then our within our error variance is going to be 261.3333 divided by 15, which gives us 17.4222. Right. And finally, to get our F observed, our F ratio for this ANOVA, we take 160.2223 and divide by our error, which is 17.4222. And we get roughly, around here, 9.20. Which what that means is our effect, our mean, our average effect variance, the difference of the squared difference of the means around the grand mean, the sample means around the grand mean, that effect variance is more than 9 times greater than our error variance. So I think we're going to be very likely to be able to reject the null hypothesis here. So I'm going to look at a calculator to determine if that is in fact statistically significant difference, which I'm fairly certain it will be because the F observed value is so high that it's going to be pretty far out there on the distribution that the proportion of the area under the curve to the right of that F value is going to be very, very small. In other words, this F observed value is very unusual, has a very low probability if the null hypothesis is true, so we're going to be very likely to reject the null hypothesis. Alright, so here we have the calculator which you can access on Blackboard. We're going to go ahead and enter in the degrees of freedom. So the degrees of freedom numerator was 3, denominator was it 15? Yeah, 15. And our F observed was 9.20, which gives us a very small p-value of 0.001. So even with a small sample size, we're able to reject the null hypothesis and say that there is at least one difference between these means, right? So at least one, we can be pretty sure that one is going to be that the pizza group read significantly more books than the control group, but we want to also see, is there a difference between the pizza group and the stickers group, and is there a difference between the stickers group and the control group. So in order to do that, we're going to conduct a post hoc test. So we're going to use Tukey's test to make that comparison. So we need to compare two means, so each pairwise comparison divided by ms within over the square root of ms within over n. So ms within is 17.422. Too small there, hold on. So q is going to equal, we'll put the denominator first, 17.4222 over little n here, this assumes equal sample sizes, which we have, is 6, right? 6 people per group. And then don't forget we need to take the square root of that. So that's our error term. And then in the numerator, we're going to be comparing the means. So we'll start with the largest difference, which is 17 minus 7.33. And we can get our Q obtained, which we're going to compare to a Q value from the table that's linked in the slides. So I'm going to go ahead and open that table and see what value do we need to get to be significant, statistically significant. So we're going to leave the overall alpha for our post hoc test at 0.05. And 0.05, we're comparing, we have 3 groups, so there's 3 means, and our degrees of freedom error, that's DFE, is 15. So we find where 3 intersects with 15, so we need to get to Q of 3.6734 or higher in order to reject the null for the post hoc comparison. So our Q critical is 3.67. So we'll put Q critical equals 3.67. Now it depends how you set this up, whether it's going to be positive or negative. I'd set it up so that it's always a positive value, so the higher mean is to the left. But just in case you don't, we can just say, okay, absolute value 3.67 is our critical. So we take 17 minus 7.33. That gives us 9.67 in the numerator. And then in the denominator, get our error term, we take 17.4222, divide that by 6, and take the square root, and we get 1.7040. So that's 9.67 divided by 1.7040, and we get 5.67 for that comparison, which is well above our Q critical value. So we can reject the null hypothesis and say that there is a significant difference between those conditions. So what we can say is that the pizza group read significantly more books than did the control group. So now let's compare the next largest difference. So going back and looking at our means, we'll compare the pizza group and the stickers group. So that's going to be 17 minus 9. Everything else in the equation is going to stay the same. We have Q equals 17 minus 9 over, so we don't have to do this math on the bottom again, we already have it, 1.7040. So 17 minus 9 divided by 1.7040 gives us 4.69, which is also going to be statistically significant according to our alpha, because it is greater than 3.67. So we can also say that the pizza condition led to significantly more books read than did the control group. So those panned out. So now we would want to do the final comparison, which I don't think is going to be significant, but we better check, is going to be to compare the stickers and control. So I want to see, do stickers work as an effective, it seems pizza sure is being effective at causing these imaginary children to read books, but what about stickers? So we're going to take 9 minus 7.33 to get our final Q observed value, 9 minus 7.33 over 1.7040. And we get only 0.98. So that does not exceed our Q critical, so we cannot say there's a difference. So what we would conclude here is that the pizza group condition led to significantly more books read than did the stickers group and the control group. However, there was not a statistically significant difference between the stickers and the control group, right? So we've done all pairwise comparisons. We've thoroughly explored where the significant difference that we found, where those are between the means. Now, if that F ratio had not been significant itself, we wouldn't have had to gone on to do the Tukey's post hoc test and compute the Q and whatnot, because we could have just said that we're not able to reject the null, and that would have been the end of the story. All right, last thing I want to show you how to do by hand is to compute the effect size, which is the one we're using. Remember, it's called eta squared, which is the SS between over SS total. So all we need to do is we take 320.445 and divide that by 581.7778, and we get rather enormous effect size. These are kind of made up play data, so it's no surprise, but a rather enormous effect size of 0.55. So what that means is that roughly 55% of the total variability in this study is explained by the differences between the means. That's a lot. It's a lot. It's unusual to see an ANOVA that explains that much variability in the dependent variable, but we won't harp on that too much because these are just kind of play data for fun for us for now. All right, so I'll upload some more examples. I'll upload another example of a hand calculation, and most importantly, an example of how to compute an ANOVA in the post hoc test using SPSS. I'll upload those to Blackboard in the near future. So I thank you, and I hope you enjoyed that lecture as much as I did.